Hi guys, I'm going to be talking about properties of materials today and stress-strain curves. So quickly, it goes something like this. We have stress and we have strain. And what exactly is this?
What exactly is this?
Yeah. You don't know. Okay, you don't know. But what we're trying to measure is stuff intrinsic to the material, or just stuff about the material. Like if we had one piece of paper, we could say it's not very strong. We could say paper is not very strong. But is that because we only have a small slice of paper? Could it be the area affecting it? Is this making sense, Richie?
Yeah, this is making sense.
Okay. So we need to divide by the area to figure out how strong the paper actually is. What's intrinsic to the material. So that's what stress is. Stress equals force over area. Okay? I'm sorry about the shadow, by the way. I'm at my house in Sale, so it's a little bit different. Okay. Stress equals force over area. Now, strain. What is strain is? Strain is how much it strain? Yeah, is how much it changes in shape. Is a change in shape. That kind of makes sense? So like if I bend this, you can see it changing in shape a little bit.
Okay, yeah.
Okay? But then the change in shape, if we had a really big object, obviously it will bend more than something else.
Yeah.
So we need to get rid of how big the object is, or how long the object is, by going the change in shape divided by how long the object is.
Yeah.
Okay, so like if I pull this and if I press this, it will be the change in length divided by the length.
Yeah.
And that gives us strain. And that's how we get stress-strain graphs. Okay?
Okay.
Finally, we have Young's modulus. And this is defined as stress over strain. Okay, Richie has to go away for a second. But stress over strain. And in essence, that's because this is a way of measuring how much force, intrinsic to the material, it takes to change its shape. How much force? This is like force, strength of material. That's better, strength. So it's like how much strength of material does it take to change its shape? Okay? How much force? Force is a better word. Okay. And so if we calculate this, it would be force on area times 1 on strain, so we just flip that length on dot L. Okay? And the final concept is energy. That's a lot of concepts now. But energy is the area on the graph, so we'll get onto that later. Hey Richie, come over here. Okay, cool. Richie will be here in a second. So the key to doing these questions is not to think. The key to doing these questions is just to go through and just write down what you have and put it on your piece of paper. Okay, you ready? I'll show you how to do it, Richie.
Okay.
So read this with me.
Engineerings are testing samples of different types of steel to determine the best
You can
type.
say it inside your head, I don't mind.
Why did you say read it to you?
I said read it with me.
Oh.
Okay, so we get area equals 2 times 10 to the negative 5, right? Now, that's the length, okay?
Yeah.
Length equals 0.1. Blah, 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 sample breaks at x. There's so many shadows now. Okay, there's a force of 8 times 10 to the 3 applied, okay?
Mm-hmm.
We're looking for stress. How do we find stress? We have these 3 things here. We've already written them down. What does stress equal?
Stress equals force divided by area, so we only need F and A.
Yep. Force on area. Easy. So 8 times 10 to the 3 on 2 times 10 to the negative 5.
So it becomes 4 times 10 to the 8.
Yep. 4 times 10 to the 8.
Oh, I was right.
Okay, keep moving, keep moving. Okay, which of the following best gives strain when the force is 8 times 10 to the 3? So how are you going to do this? We want strain, which is change of length on length. Okay? Oops, I wrote that a bit funny. Change of length divided by length. Okay? We know our length.
Yeah.
So we want to know the change in length. Any idea how to get the change in length?
Do we just look at the graph?
Yeah. Awesome. So we look at the force,
Mm-hmm.
we go across, and we go down, and we get the extension there. Okay? So this equals 5 times 10 to the negative 4. Actually, you tell me what it is. I already told you that. But what's the length?
Length is 0.1.
So what's that equal?
So it just becomes 5 times 10 to the power negative 3.
Good. I was hoping you would get it wrong so I could scold you. But no. So C, okay? Which of the following best gives Young's modulus for material P? So Young's modulus is usually the gradient of this. It's the gradient of stress versus strain. But we don't have stress versus strain. What do we have here?
Force versus extension.
And what's that in our diagram? In our little formula? Force versus extension, okay?
Yeah.
That's what we have here. So the gradient gives us force on extension. To get Young's modulus, we have to divide by area, multiply by length. So I'll rewrite that. So this is the gradient of force versus extension graphs, and then you multiply by length, divide by area.
Yep.
So how are you going to do that?
So we have force and...
Up to here.
Okay, so we know that force is 8 times 10 to the power of 3.
Yep.
And you divide it by the difference, which was 5 times 10 to the power of negative.
Okay.
Yep.
Yep.
And then you times L, which was 0.1,
0.1.
divided by area, which was 2 times 10 to the power of negative 5.
Okay.
Yep.
And now we just solve that. Can you solve it for me?
Oh no.
Okay, so I'll help you do it. Okay, 8 divided by 5 is 1.6.
Why don't you just do it like this? So there's 5 times 2, so
Okay.
that becomes 10, so that you have 8 times 0.
So I did the top. 8 times 10 to the negative. So it should be
9.
negative 9, and then you multiply it by 10.
That should be it.
That should be, okay, 10 to the negative 9.
Yeah.
Okay.
So it just becomes
8 times 10 squared on 10 to the negative 8. You don't need to do these guys, but
yeah.
we just don't like calculators. I don't know how to use calculators. So our Young's modulus should be 8 times 10 to the 10.
Okay.
And that should be enough for this video. I'll go over energy in the next video. But yeah, thank you, G. Awesome.